Another example of a beam, this time with 3-point loads. We have previously worked out the reaction calculations for VA and for VB. Now we're going to plot the first of the two diagrams, which is the shear force diagram. For that, I'm going to draw in some construction lines. At the start and the end of the beam, and where each of the point loads are located. I'm going to draw in a zero line. This will be our shear force diagram, units being in kilonewtons. You're going to start off at 0 on the left hand side. From the left hand side, we're going to reveal the beam and we're going to add up the total force that we actually have as we progress from left to right. Starting at the very end of the beam, start off at 0. The first force we reveal will be the first reaction, 27.92, and that will cause us a jump up to 27.92 kilonewtons. As we move through the first section of the beam, the total force stays the same at 27.92. Until we come to the first point load, 25, that will cause a drop of 25 on our current value, taking us down to a value of 2.92. As we progress through the next part of the beam, the total shear force from the left to our point that we're considering stays the same at 2.92. Come to the next point load. Ten kilonewtons. That will cause, it's pointing downwards, so will cause a further drop of 10 on our current value of 2.92, and will take us to a value of minus 7.08. Move through the next section. The total force from the left stays the same at minus 7.08 until we come to the point load, the 5 kilonewtons, and that will cause a further drop of 5 to give us to a value of minus 12.08. As we reveal the last part of the beam, our shear force value stays the same at minus 12.08, and finally the last reaction, which is also 12.08 pointing upwards, it will cause us to go back to close off our shear force diagram at the value of 0. And that's our shear force diagram drawn. To draw our bend moment diagram, we need to consider the areas we have on our shear force diagram, namely each of these rectangular areas. So to get the value for our bend moment points, we need to calculate these areas. Simply the height on the shear force diagram multiplied by the length. The lengths are given 0.5, 3, 1.5 and 1. So to calculate the areas, we will do 27.92 times 0.5, and that gives us an area value of 13.96. Our green area has a value of 13.96 kilonewton meters. For the blue area, it has a height of 2.92 and a length of 3. So the blue area has an area value of 2.92 times 3, and that should give us a value of 8.76 kilonewton meters. For the red area, the height minus 7.08, the length in that case is a value of 1.5, so the area value here is minus 7.08 times 1.5, and that has a value of minus 10.62. For the last yellow area, it has a height of minus 12.08, a length of 1, so that gives us an area value of minus 12.08. 13.96, 8.76, minus 10.62, minus 12.08. Before we draw each, or the bend moment diagram, we're going to do a quick check on these areas by adding them up. Pay attention that areas beneath the axes will be negative. Add up our values and we get a value of 0.02, for all intents and purposes is equal to 0. The reason why we don't get exactly 0 is due to rounding of numbers. That then gives us confidence then to go ahead and to draw our bend moment diagram. First of all, I'm going to draw in some construction lines, and this will coincide with the start and the end of the beam and with where each of the point loads are applied. Draw in a 0 line, and this will be our bend and moment diagram with the units given in kilonewton meters. To plot points on the bend and moment diagram, first of all, what we're going to consider is the area we have enclosed in the shear force diagram. Starting off on the left hand side, revealing the beam to the right, first of all we have 0 area on the shear force diagram. As we move to the first point load, the total area revealed is the total green area, 13.96. As we move across the beam to the next point load, the total area we have revealed on the shear force diagram is the total of the green and the blue areas. Those two values added together, 13.96 plus 8.76, gives you 22.76. Next, move across to the next point load. The total area we have revealed on the shear force diagram are the addition of the 3 areas we have, the green, the blue and the red area. Careful, the red area is negative, so effectively you'll end up taking it away. When we add our 3 areas together, we get a total of 12.1. Then at the end of the beam, to plot our point at this location, we add our 4 areas together and effectively we get 0.02, or for all intents and purposes 0. Now what we have to do is to join the dots we've plotted on the bending moment diagram. In the first region, we're going to consider the shear force value constant at 27.92. What that means is we have a line of constant gradient. The gradient of that line is equal to the shear force, 27.92. In the next region, we have constant gradient or constant shear force again, 2.92. In this region, we would have a line of constant gradient. The gradient of this line being the value of the shear force, 2.92. In the next region, here, your shear force value is minus 7.08. Again, constant, so we have a straight line. This time the shear force value is negative, so it means we have a straight line, but the line is going downhill. Here the gradient is minus 7.08. In the last region, our shear force value is constant, minus 12.08. Again, we'll have a straight line. Again, negative gradient, so it's a line going downhill. That gradient will be minus 12.08. And that is our bending moment diagram drawn. Point to note, maximum bending moment is 22.76 kilonewton meters at a location which is 3.5 meters from the left hand side of the beam. Then zooming out to see the shear force and the bending moment diagrams together, you can see the resultant diagrams.